and the book by Erwin Bolthausen on perceptron version of the generalized random energy. I hope we shall hear the definition of what it is.
Okay, so thanks you for the introduction. That's a joint paper, recent joint paper with a former PhD student of mine who is now at the University of Bonn. It's a somewhat artificial. I first have to apologize. Okay, it's on random media, but it's not on dynamics of random media. It's a somewhat artificial model. I hope I can get a bit of motivation for this. Yeah, it looks very artificial model. But the main issue was to understand some things on a rigorous level in spin glasses, which cannot be understood, say, for the generalized random energy model. And one of the issues, there are several issues which are much more complicated than in the generalized random energy model, but where we can prove things rigorously. And these things cannot be proved yet, say, for more common spin glasses like the Sherrington-Kirkpatrick model. So for that reason, I think I hope that one learns something from the model. Also, it is still far away from, say, even mean field spin glasses like the Sherrington-Kirkpatrick model. So I start with the Ruel's probability cascade. So first in the additive fashion. So there one has k levels, and one has a set of parameters. So for convenience, I take them ordered upwards. And then on the first level, one just given by Poisson point processes on the real line, this real probability cascade. So on the first level, one just takes Poisson point processes on the real line, so which have an intensity measure. Now the intensity measure is having an exponential decaying, it's exponentially decaying. So what you are getting you are getting countably many points, random points on the real lines, and because of this form here of the intensity measure, one has a maximal point, and then you have the second, etc. But you have countably many, so they are getting denser and denser if you are going to minus infinity. So that's just because if t goes to minus infinity, this is growing. So that's.
Where is the t then? I don't.
Yeah, that's just the intensity measure. So it just gives you. You see, if you have an interval, you just it's the number of points in this interval is given by a Poisson distribution with a parameter which is the integral over this intensity measure. So that's just this Poisson point process. So is that clear what it means? Yeah.
Is it t the axis?
Yeah, t is the axis. Yeah.
T is the axis.
T is the axis.
So the top point would have the smallest. Typically would have the smallest.
Now you see that goes to this is exponentially decaying. So to it's integrable at the positive on the positive side. So you have a maximal element. So that's you only have finitely many points. So at every point. So if you take the interval upwards, you only have finitely many points. So because you see, if you fix a point here, and you look at the interval to plus infinity, so the number of points in this semi-infinite interval is given by the integral over that. So over this integral. So it's finite.
So I imagine that this interval goes from 0 to infinity, do I? Yes.
No, from minus. Okay, I take it for the moment. I'm taking it on the real line. So it's on the real line. So.
But so far only R1 is involved.
Yeah, for the moment. Okay, that's the first level. So the next slide gives the second level. So etc. So. Okay, so the next level is you see to any point to any point on the first level you attach an independent Poisson point process with this intensity measure with the next parameter. So with R2. So this is you see you're attaching to say that's maybe the second point on the first level. You're attaching a whole Poisson point process here. So, and independently to this point, you are also attaching a whole Poisson point process on the real line. So with this intensity measure, and then to every point on the second level. So that can also come from this here. So you attach again a Poisson point process on the real line. So with the next parameter, etc. So now formally you see the points which are formally the energies. they are, say, you can order them downwards because there is a maximal element. So on the first level, you have a biggest one, which is just a random variable x1, and then x2, x3, x4, etc. And then every point here, you are attaching a new sequence. So say, for instance, this would correspond, that's a second, so this would correspond to I equal 2, and then again you can order them downwards. So, but for every different I, you are getting new point processes. So you are getting a whole cascade of these point processes here. So that's, is that clear?
No.
No.
So you have infinitely many. After the first line is.
You have infinitely many point processes on the second level. You have then.
With the intensity R2.
Yeah.
And then.
Yes.
But then this has only k steps. This
Yeah.
process.
You only have k steps. You have k steps. So in the end, okay, that's then. If you want to make a model with infinitely many steps, okay, you will see that how in principle you are doing that. So but for the moment, you have just k steps.
Right.
But even for 2 steps, you have infinitely many point processes. Yeah.
But then, will it be important that you have k rather than 2 steps?
Yeah, it depends what you mean by important.
Yeah, well, if there is a
for explaining the effects, there's no importance. But if you see these cascades are supposed to be to model so the Gibbs distribution for the Shenton Kirkpatrick, and in effect you have to go let k go to infinity.
Yes, and it is. Yeah.
Okay, what you are doing is that you can sum up all the, okay, for that reason it's called the random energy model. So you're summing up the energy on all the levels. So you see this I, this bulk phase I is I1, is I1 up to IK. So okay, I should have written it somewhere. So the bold I is just consisting of k components. So maybe I should write it here. So I bold is just I1 up to IK, and to this you attach, say, the energy on the first level, where you take just the first component of I, and then you add here the thing which is on the second level, etc. You're summing that up here. So in that way, you are just getting countably many points on the real line. And you can form the point process. You just it gives you a measure on point configurations on the real line here. So, and okay, you see in the end. So these random energies, they are just a point process here. Okay, in principle they could be dense, but in the case we are having here at hand, because we took the parameter properly. So this is just a countable set of discrete points you are getting this way. And then you can attach to that backwards clustering. You see, if you're just writing down the point, you have completely forgotten the whole hierarchy. So you are, of course, it's just a countable number of points. You can take the biggest one, the second biggest one, etc. You're going down, but you can still attach to them the indices. So the multi-indices from which they are coming. So for instance, say the biggest point here in the whole collection is coming from taking the second biggest on the first level, the biggest on the second level, and the third biggest on the third level, etc. So in that way you can of course to any point attach this multi-index here I, and then you can define the clustering. So you cluster first the ones which are agree, say, on the first 2 levels. So here, for instance, this point and this point are having 2, 1. So that means they are coming from the first. They are agreeing on the first 2 levels. And so that you cluster them together. So then, for instance, then these 3 points here you cluster together on the next step because they agree on the first point here. So, but after, so maybe in the end you cluster everything together. So in that way, for instance, if you have 3. K equals 3, you are having, if you are going backwards, you are getting okay, You can describe the whole thing as a point process on the real line and this backwards clustering, so which are running with k levels. If you have a k level real cascade here, so the outcome is a point process on the real line plus a random clustering process. Yeah. So,
Is the number of levels fixed? Like
yeah, I take the number of levels fixed. So k is fixed. So you know what I'm doing for them. Yeah. In the end, you can easily you will see it. You can generalize the models that the number of levels is no longer fixed, but for the moment everything is fixed. That is originally Ruel's description of these cascades.
So it could split by 2 at each level or something like that. Like here you have a splitting of 2.
3.
You have a tree in every.
Yeah, you just get the tree. So k level 3. So if you look at now going closer, this should be this random energy. And then you're constructing the Gibbs distribution. So that was this Ruel's version of maybe Derrida's first version of a spin glass where you take these random points as the energies. So as these random energies, and then you're going to the Gibbs distribution. Of course, I should write a minus here, but the physicists always write a minus. I write it in this way, and then you're getting, say, the unnormalized Gibbs weight. So, and then now this requires that beta is large enough. You see, if beta is large enough, you can prove, and actually beta has to be bigger than RK. So the last parameter. You remember I had this sequence of parameters: R1 for the first, R2 for the second, etc. RK for the last level. So, and if beta is large enough, actually you can formulate it also. You have to modify it slightly if beta is not bigger than RK. But if beta is bigger than RK, you can. It's easy to see that the sum here over the energies here is finite almost surely here. So you can normalize it, and you're getting normalized Gibbs weights. So normalized random Gibbs weights here, which I wrote here by this hat here. So for instance, if you do it for the first, if you just do it for k equal 1, where you just have one level, so then you look at the point process of these normalized objects here, and then you get what is called the Poisson-Dirichlet point process, which has parameter r divided by beta. So I write it as PD r divided by beta. So that's this Poisson-Dirichlet point process. Now, there are some surprises here already, but they are easy to check here. So if you have k levels, then nothing new is happening. So on this point process level. So because if you look at, you see, the point process, say, if you don't normalize it, you don't you get something which is depending on this number of levels. So the distribution for the unnormalized Gibbs points, you are getting an object which is depending on these k levels. But if you normalize it, the dependence on this k level is just dropping out. So what you are getting, that's at first a little bit surprising, but you can easily do the computation. If you look at the point process, say, of this k level generalized random energy model, this is just as if it would come for k equal 1. It's the correct parameter, so RK divided by beta. So you get, so you see at first it looks that it doesn't get, these k levels don't get any information on the point process level. So, but of course you can keep track of the clustering which I have defined before, because of course this clustering is also defined for the point processes of this normalized Gibbs measures. So you can just take over the clustering you are having, and then, but somewhat surprisingly, this is the attached clustering process is stochastically independent of the points of the point process. This is quite a surprise if you first see it, but the computation is easy to do so. Now that's it. Okay, people call it now, because this formulation came up in a paper I had written with Alain Snitman, so people call it now the Bolthausen-Snitman correlation. So what you are getting here is a point process, which is just a Poisson-Dirichlet point process, and that attached clustering is independently attached correlation process here. Now this is okay. This is just coming out here from this real cascades, but okay, this is now okay. People claim that this is just the fact for essentially, at least for mean field speed classes, all kinds Sherrington Kirkpatrick or whatever kind, that this is always the picture which is coming up in the limit. So this is a totally universal structure which should pop up in mean field, at least mean field type spin classes, and I think many people also believe that at least maybe with some modification. Okay, that's a hot debate here. That it also something of this kind is true for say maybe short-range spin classes. So but that's very controversial. Okay. Is that clear? How this is constructed?
What is surprising about that?
Yeah, surprising. First surprising is first that for the point on the point process on the normalized Gibbs distributions you don't see okay, it's just as if it would come from one level, and secondly that the attached correlation process is stochastically independent of the point process. That is okay. When I first realized it, it was a bit of a surprise. So it's actually depending very much on the spatial form of the intensity measures. Also,
so with a different intensity measure.
Yeah, no, it's totally true. It's totally wrong. Now this now a crucial thing, and this plays a big role. So also recently in the recent work by Michael Eisenman, Arga, and other people is that this you see the reason people might be one of the reasons that people believe that this structure is appearing universally in these spin classes is that you have a certain invariance property under cavity, what people call cavity transformation here. So that's oops, maybe now this okay. What is this invariance property? So you start with such a real cascade here. So you're having, and now you maybe okay. Maybe I should say something about the motivation of this cavity transformation. This is originally was coming out so in this Parisi-Mizar work on the Sherrington Kirkpatrick model, where they considered a system, say a Sherrington Kirkpatrick type model, so with n spins. And then they were adding one spin here, and they were looking at the effect of one spin adding to this n spin system, and they were looking what is happening, say with what kind of transformation there appears if you're just adding one spins. Now the point is that if you go over to these real cascades and do this one spin transformation, then the whole structure is invariant under this transformation now. But the cavity transformation is really motivated from the Sherrington Kirkpatrick model, which I'm not presenting here, so in any details here. Now what you are doing is that you are adding what people call Gaussian cavity variables. These are just Gaussian variables which have a certain covariance structure. Now this covariance structure is you see this for every of these multi-indices here you are having these cavity variables, and then it has a covariance structure which is just coming from essentially from the overlap structure of this k-tuple I. So what you're looking is okay, you call that the overlap. So if you have I and I prime, you're looking at the maximum J on which they agree here, and you're the Gaussian variables, so you're just constructing a Gaussian field with these cavity variables, and then consider the new Gibbs weights. So here we have the old Gibbs weights, and you're just multiplying it with e to the beta. Okay, it should be a minus, but I'm always writing in this way, beta, and then this sigma is a new spin variable, so it's -1 + 1 here. So and then you're having these cavity variables. You see, if you would look at the Sherrington Kirkpatrick type model, you would get exactly, this term would exactly correspond from changing the energy of adding one spin. So sigma n + 1, say. You just would get, now if this would be the Gibbs weights, maybe unnormalized Gibbs weights before, so you're just multiplying it with this factor, which is just the effect of adding one additional spin. So you're ending up with that here. And the yi's would come from the interaction strengths in this Sherrington Kirkpatrick model of the newcomer, which is here this sigma, which would be sigma n + 1, with the old ones here. So now you of course here you can sum out the newcomer sigma, which is just gives the modified unnormalized Gibbs weight, which okay, you're just getting of course the cosinus hyperbolicus times 2, and so you're getting, say, the new Gibbs weights on this I here, which are just that here. So now the somewhat surprising point is that the whole structure remains invariant under this cavity transformation. What you can do, of course, is you're getting these new weights. This gives you, after normalization, it gives you a new point process. Okay, you get this new point process. You can normalize it. You get new a new point process, which of course is a random probability distribution. So because you have normalized it. But then you can also keep track of the overlaps which you had before. So you completely reshuffle things, and the crucial thing is this theorem, namely that the joint law of this object with this reshuffled clustering process remains the same as it had been before. So that it's now a big issue to characterize, to prove that's a program Michael Eisman had made propaganda for I think 20 years, to prove that the whole structure is characterized by this property. So namely that it is invariant. He had the papers with Rusmaikina and Michael, and then more recently, Rusmaikina and Eisman had a theorem that characterizing this object in the case where you just add independent things, where you have essentially one level. So just if you have independent cavity variables. So and then later, there is some newer work by Augin and Michael Eisenman and then Panchenko. So I think at the moment it's not totally proved. So, but there are steps in this direction proving that the whole structure. So with this point process, with this overlap structure is characterized by this invariance property. Now, in order to go into the direction what we did, really I have to step a little bit back also in history, namely the real probability, the real generalized random energy model was actually coming out originally from a finite n random energy model invented by Derrida. So that's a finite. There you have a model which doesn't have infinitely many energies, but has only finitely many energy. But it's also organized in a hierarchical way by k levels here. So now on every level you have just say in the end I want to have 2 to the power n random energies, but like a little bit in the Shelton-Kirkpatrick model. You want to copy a little bit the situation for the Shelton-Kirkpatrick models where you have 2 to the power n spin variables. So I'm taking 2 to the power n divided by k random energies on every level. So totally I will have then in the end 2 to the power n energies. And on the first level I just take x11 up to x1 2 to the power nk. And then on level 2 I'm taking for every I1 I'm taking again 2 to the power nk, etc. random energies here. And the assumption is that the xm, for this, the m is for the level I'm in, they are Gaussian with a variance, and the variance is proportional to n. So everything is a bit copied from Shelton-Kirkpatrick, because the random energies in the Shelton-Kirkpatrick models are also Gaussian random variables with a different covariance structure from that here, but which are proportional to n here. So. And then, still there's a parameter which depends on the level here. So I have a picture on the next slide where you perhaps see that better. And the variances, that's just convenient. So it's not essentially, the variances are ordered downwards. So the first level gets the highest variance, the second level gets, etc. They're ordered downwards. It's easy to take care of if that is not satisfied, but there are some slight complications here. So, and for convenience, I assume that that will sum up to 1 here. And then the total, for this Derrida generalized energy model, so the total energy is just again given by this sum here, essentially as before, where here this index is of course, you have 2 to the power n possibilities here. And then you look again at the finite n Gibbs distribution, which is just, of course, given by that. In principle, you should have that minus here. So, and the partition function is, of course, just that. So. Now, again, as above, one can just consider here the point process. Now, that's just a point process with finitely many points, and you can also keep track of the overlap structure here. So, and then, okay, I still have a picture here, maybe a bad picture. You see, okay, you can write it as a tree, where you have a k level tree. So, but on every, you see, on every level, I have 2 to the n divided by k branches. So, and then you can think of attaching to the bonds of this tree. You are attaching, say, on the second level, corresponding here Gaussian random variables, and the total energy is just the sum. Okay, the configurations at the ends are just the points here at the end, and then you just sum along the tree. You're summing it. So that is a pictorial picture of this Derrida's generalized random energy model. No, and then there is you see, okay, that maybe the real took that more or less for granted, but it actually takes a little bit, it takes some work to really prove it. So that had been done by Bouvier and Kurkova, so a couple of years ago, namely really mathematical proof that the thing converges to this real cascade. So namely that, okay, you have to assume that beta is large enough. In that case, it's bigger than log 2 divided by the square root of ak, where ak was the variance of the last. You see, I had assumed that the variances are ordered downwards. So on the last level, they have the smallest variance here. So and then beta has to be large enough. So then you can easily modify it if this is not satisfied. So, but that's a simple situation here. So then the point process with the attached overlap structure converges. Okay, you have to say properly in which sense it converges. So it converges weakly to a Poisson-Dirichlet point process with attached correlation here. So that it converges. So the case is the Derrida model converges properly formulated to this real cascades here. So that's the situation here. Okay, now the situation is actually okay. The picture is quite simple, and I'm putting some emphasis on that because this is important for what I'm talking later. So you see, if you just have k equal 1, that was the original random energy model by Derrida. Now in that case, the Gibbs measure concentrates if beta is large enough. So what is happening is that the Gibbs measure concentrates on the maximal guys here. So just the one which have the maximal energy. So the real maximal one, the biggest energy is getting a random weight. So, and the second biggest is getting another random weight which is smaller. But that is the situation. So always the Gibbs distribution concentrates on the maximal guys. So if beta is large enough. So now it's similar for if you have more than one level. So then what is happening that is the Gibbs concentrates on those configurations which on the first level the energy is maximal or second maximal or is among the maximal ones. And then you choose among the ones which are close to the maximum. On the first level you choose, you branch off and look then at the ones which are maximal or close to maximal at the second level, etc. So the Gibbs distribution is really concentrating. If you want to look if you want to find out which configuration contribute to the Gibbs distribution in the limit, you just go look which one is maximal at the first, maximum, second maximal, etc. is at the first level. Then you look at the things which branch off at that, and then you look at the ones which are maximal or second maximal, etc. on the next level, etc., etc. So that's the situation here. Now this has the consequence that this model doesn't have what people call the count property, which by people in spin glass theory, non-rigorous spin glass theory, is claimed to be universally true, more or less, in spin glass theory. Namely, the point is that, say, if you choose here, say, the index according, say, to Gibbs distributions at the temperature beta, and you choose, say, a second independently according to a Gibbs distribution which is at a different temperature beta prime, then you see you are still in the situation where essentially you're just picking up the things which are at the maximal level here. So, and then if you look at the overlap, so how far you have to go back here so until they agree. So this is still a random variable. So if beta is equal to beta prime, if beta is equal to beta prime, this is given. This law is given by the law of this correlation process here. So, but if you change, say, one temperature a little bit, then it's of course the distribution is essentially the same. Okay, it's changing continuously. So that is totally contradicting what physicists claim. So it's this chaos property. Namely, physicists claim that if you change the temperature parameter, things are completely reshuffled, and then the overlap is becoming is getting non-random here in the end. Yeah, this random energy model I have introduced here, or this generalized random energy model, does not have this chaos property. This is actually at first sight it's quite puzzling. So because it's people, you see, for instance, if you're looking at Kirkpatrick model or at similar models, so people are often drawing the picture that you have this you have this energy surface with these many valleys, and then as you say, the Gibbs distribution is concentrating, say, at the bottom of these valleys here. So for instance, you have the ground state, and then on the ground state, of course, you're looking at the bottom of these valleys here. So, and then so somehow the picture I originally had, but this picture is completely wrong, is that if you have a finite temperature, then you are still in these valleys. But of course you're changing a little bit the distribution. So, but this is completely wrong. So because if you change the temperature, the thing is totally reshuffled. So the original, the guys which are contributing, say, to the ground states have nothing to do with the guys which contribute to the Gibbs distribution at another temperature. How low this temperature is.
Well, have you an idea of the sensitivity to the temperature?
What?
Can you make it in some way quantitative? What is the overlap of the configurations when you change the temperature by epsilon?
For this Graham model? Yeah, that you can do. So that's an exercise on these cascades to.
No, for the Shannon-Kirkpatrick model.
Wow, okay, for the Shannon-Kirkpatrick model, this is not proved anyway. So that's nothing. For the Shannon-Kirkpatrick, you can do the computation, but I think this is not a.
How is this hierarchy? Can you do it?
What?
The Vulcan symmetry of Paris. Can you do it then?
Yeah, I think you can do the computation. I've never do it. But you see, the claim is that if beta is different from beta prime, then the overlap is constant. It's no longer random. So if beta is equal to beta prime, then the overlap distribution is given by this cascade business. Of course, it's in the Shannon-Kirkpatrick you have a complicated. You cannot effectively do it because, for instance, for this, you don't know if there is a unique Q function. So the Q function which is appearing as an order parameter, functional order parameter in the Shannon-Kirkpatrick model satisfies the differential equation, and nobody can prove that it has a unique solution. So, but modulo this fact, you can do the computation. Yeah. Now from this, all that is just maybe a kind of a motivation also for what we were trying to do. It's obviously that the cavity transformation, say, of this generalized random energy model, of this finite n generalized random energy model by one spin, is not giving anything interesting. So now what we were trying to do, what our model, the aim of our model is to cook up a model which is not as simple as you see. The generalized random energy model is perhaps too simple. So, and the Shannon-Kirkpatrick model is too difficult. So nobody can prove this hierarchical business up to now. Also, people have tried very hard. For instance, Talagan have worked on that for 3 years. So to prove something like that for the Shannon-Kirkpatrick model. Now, what we were looking up is for a model which is a bit artificial, but where interesting things are happening and where we can prove that these interesting things are happening, which are more complicated than in this than the situation.
Is this related to the ultrametric or not?
Yeah, sure. You see, this ultrametric, you see that's this goes farther than the original ultrametricity conjecture. So the ultrametricity conjecture just says, for instance, for the Shannon-Kirkpatrick model, you just pick 3 guys independently according to the Gibbs distribution, and you look at the overlap, and then you say, okay, as n go to infinity, this gets ultrametric. So the real prediction is much more precise. So it gives really. It tells you that if you pick say independent copies of the Gibbs distributions, so the distribution of the overlap comes out from this correlation process. So this is you see the claim in theoretical physics about what is happening is ultrametricity with really more precise information, namely given all this essentially that always is real cascades, or if you look backwards in this with this clustering mechanism, with this correlation process is coming up. Now the question we are addressing is that if we would look what happens if you start with a finite n generalized random energy model, but we don't make a cavity transformation with one additional spin, but with macroscopical number of spins here. So that was what we are looking at. Actually, there's a lot of motivations behind. That was always my idea. That you see people looking at this also for doing this cavity method in say for the Sherrington-Kirkpatrick models. They're always adding one spin, or two spins, or something like that, and they're investigating what is happening. I think it would be a good idea to add say a small macroscopical portion of spins and see what is happening. I think, but that I have not yet managed to do anything in this direction. So what we were doing is that we were taking this Derrida generalized random energy model, and we were adding a macroscopic number of spin variables here. So I call them rho times n. It should be here rho times n, not r times n. So
in the cavity approximation, usually you solve it without a particular spin, and you compare that with the spin added.
Yeah.
And then you're talking about a model where you have a lot of spins that are removed and then added in.
No, what I'm doing is just I'm adding a portion of n newcomers. So and I'm coupling it together. So I'm just look at this Derrida's version of the generalized random energy model, and I add say proportional to n spin variables, and I look what is happening with the structure. So the point is that now we can completely analyze that in all temperature what is happening, and I think something interesting is happening. So maybe it looks a little bit at first sight artificial, but okay. So what our Hamiltonian is saying, I take the Hamiltonian of the original generalized random energy model, and then we add here this where this Yij. Okay, the sigma i's are just plus minus one spins, and this Yij's are these cavity variables. So they are Gaussian random variables, which have the following covariance structure. So if J is different from J prime, they are independent. So, and then they have an overlap structure, which is you can take a monotone function of this overlap, which is coming from these i's here. So, of course, you can represent these cavity variables by independent Gaussians. So these Yij's, you have the first level Y1 I1J, and then on the second level Y2 I1 I2J, etc. It goes on in this way. Now they should have variance. Now this is just of order 1. So these cavity variables have variances of order 1. So for convenience, I assume that they are ordered downwards here again. I can take them together in a vector here. That's for later use. I can also take this cavity. Okay, the cavity variables here are really these ones, but I can take them together as a vectors here. So as a cavity vector here. So which has as many components as you have levels here. Now, in that, you can easily convince yourself. So if you, for instance, look at the metric, which is introduced by the L distance of this Hamiltonian, so that's not an ultrametric in that case because of the appearance of this sigma i's. But in principle, you can you see, for instance, that the partition function is then just given by okay, you're summing over i's and the sigmas and then this object here. But of course, the sigmas you can sum. Okay, maybe I go back here. So there you have the Hamiltonian by that, and then of course the sigma variables you just can sum out here, which gives you cosinus hyperbolicus. So you get something of this type here. So you get, okay, that's rho times. You're just getting this. You just get this expression here. Now the main result is that this cavity transformation. Okay, that's the model we were looking at. So the main result is that this cavity transformation of the generalized random energy model that leads in the limit to a real cascade with a non-trivial transformation and an algebraic structure of the. You see what you get is really, we can prove in that case that this model is in the end, so it gives the real cascade with an overlap structure, so with this correlation process, but the structure you get out is depending in a highly non-trivial way on the, say for instance, on temperature parameter and things like that. So you really get, you see, if you just add one spins, you don't get any transformation because you have this invariance property. But if you add here this macroscopically many spin variables, you get a non-trivial transformation. Actually, a transformation which we can, in most cases, we cannot really characterize completely. So, but you get a non-trivial transformation of the structure of the generalized random energy model and of the parameters here. Now, what you also get is that you get the chaos property here. So I can explain that. So you get this model has a chaos property, and I believe that you see in the proof of the theorem, it's quite non-trivial to prove it because the appearance of these cascades is coming up in a rather complicated and delicate way. So I believe that. It tells you something about the real problems in spin glass theory. Also, it's certainly a quite artificial model here. So. Now, for simplicity, I take here the rho equal to 1, and I'm leaving out that part here. So the original energy part for the generalized random energy model here. That you can easily include in the end here, and the rho equal to 1 is just for convenience. Oops. So what we get is a Hamiltonian of the form here, where you have, say, okay, I just sum here from, okay, originally it was rho n, so I'm just summing j from 1 to n. And then I have these cavity variables here, and okay, still the temperature parameter, and then a function f. So this f, okay, originally, from the original cavity transformation, it was log cosinus hyperbolicus, but we can take an arbitrary f. Yeah. So I even make it more general a little bit later here. Where the cavity variables are given in this way, so just as written before, just a sum in this hierarchical way. It's appearing here. Now, just why do we call it a perceptron? So we call it a perceptron because it's very much related to the perceptron which was much investigated by Talleyrand. And if you have a chapter in his book, and maybe 3 chapters in the next book he's writing. So the perceptron originally investigated, but okay, the perceptron is something coming from neural computing. So the original perceptron was a problem that you're asking. You have an n-dimensional space, and you ask, and you're drawing in the n-dimensional real space. You're drawing, say, a number of proportional to n random half spaces, and then you ask how many points on plus minus 1 of among the points plus minus 1 to the power n are in the intersection of these half spaces. So that was the original problem, and it is related to this perceptron in neural computing. So okay, Talleyrand started to investigate a soft version of that. Okay, I don't explain why it is related to this combinatorial problem here. So what he had was a Hamiltonian which was given in the following form. So the sigmas are here from -1 to the power n, and he has a function f, and then he's summing from j equal to 1 to, say, proportional to n, or it can be n. So, and of a function at the beta times these cavity variables here. But here the cavity variables, you see, in our case, the cavity variables are really coming with this hierarchical structure from the generalized random energy model. But in Talleyrand's case, they are coming from the -1 to the. It's more of the Shannon-Kirkpatrick type. Now I have forgotten probably. No, here they are. So these y sigma i's are given then. Okay, they are Gaussian random variables, but with a covariant structure, and the covariant structure is just given by the overlap of sigma and sigma prime. So you can represent it in this way. So you sum here the sigma g. So these are standard normalized Gaussian random variables, and you just sum here from I equals 1 to n g I j sigma I, and then you're getting this model here. Now, on this model, I think it's a quite interesting model. You cannot apply the tricks so by Guerra, this interpolation tricks for this model. So there's a lot of work essentially by Talleyrand on this model. Where
What
he
do you want to
proved
know about that model? What's
essentially, okay. He has a lot of results and more results in his forthcoming book about that. But he cannot really do anything in high temperature. In low temperature, sorry.
What would you like to do?
No, just a full policy formula. Full policy formula. So for the policy type formula. So up to now, essentially everything one knows about that is high temperature. So that's small beta. So, but they are okay. It's already in high temperature. It's an extremely non-trivial model. So
what do I do? I take that and
okay, that's just Hamiltonian, and you look at the partition function, and you want to determine the limiting behavior of the partition function. Yeah, and you want to probably there is a. I'm not even sure if there is a. Probably you can do replica computations. I haven't looked at that. Okay. I think, okay, but that's a personal opinion of mine, that this perceptron is really the core of spin class theory. If you understand the perceptron, then you understand spin class theory. But that's a little bit personal belief. Anyway, so what we have is of course just a generalized random energy model version of this perceptron. You see what is the difference between that and the original random energy model, or the generalized random energy model. The generalized random energy model has just F equal identity, so that's it. So, but having F not equal to, you see also in this perceptron here, if F is identity, that's trivial. So the real issue is really that you have more general functions F here. And taking F here, non-identity, is really making a big difference. So that's okay. Now I see I'm running out of time. So as usual, I still have 9 pages. Okay, I explain. Okay. Something which really came as a surprise to us, and which we never had expected when we started to look at that, is that if you compute the free energy, you can compute the computation of the free energy. You see, the real difficult issue is really to prove these cascades. So the existence, appearance of these cascades, because that's really the okay. That we succeeded just recently. Most of the things I'm talking here about is 2-3 years old. But we had serious difficulties to really get out the cascades, to prove these cascades, because that's much more delicate than to do the free energy. Now, but already the free energy came quite as a surprise here. So the first step when you do the free energy is something which is quite similar to what you do in large deviation theorem. What large deviation theory? So we first proved a kind of Sarnoff type theorem, which is in the end giving the free energy. So I just want to explain that quickly. So what we were looking at is we looked at, say, the empirical distribution, in statistics is sometimes called the empirical distribution of this cavity vector here, so of this cavity vector. And then we looked at the more, it's just conceptually, it's easier to look at something which at first sight looks much more general. So than the model we were looking at. Namely, what we were looking at is we took this empirical distribution and we looked at, say, a continuous maybe, but nonlinear function. You see, that's a random probability distribution on r to the power k. So we looked at the function. That should be a double point, not equal. So phi is a function from this space of probability distributions to r. Now the original problem, so without the green part, was just where this h is this linear function of this mu. So h of mu is this linear with this low-cosine hyperbolicus. But then we looked at these more general objects. So because just if you're okay, I'm originally coming out. I have worked a lot on large deviations. So from this large deviation point of view, it's actually conceptually easier to look at this more general object here. And for this partition function, we came up with this Gibbs variational formula, which is quite similar to what you have in standard large deviation theory, except you have one difference. You get the supremum over the mu's, and this h of mu, this functions, minus the relative entropy. Phi is this product of this Gaussian distributions, plus this log 2. So that's the usual relative entropy. But it's important that you have a restriction. Now this restriction leads to something interesting, I think. Now the restriction is just that, you see, typically in the Sarnoff type theorem you would just have that without these restrictions, but what is coming out is if you take this mu and you look at the marginal on the first k components, and here also the marginal of the normal distribution on the first k component, you need this restriction here. So for any k on any, and then now this restriction lead to some. I'm really now getting out of time. So this restriction. Oops. Now if you specialize to something which is linear, so in view, like in the original problem here. So like in the original problem, where we have, let me see, where this h of mu is something linear in mu, you look at something which is linear in mu. So this Hamiltonian is then given in this form here. So what you get is that the influence of this restriction I have shortly written here leads to a formula which is very close to the original Parisi formula. Namely, you define in a complicated way a sequence of functions which start with the highest level, but that should appeal only to people who have seen the Parisi formula popping up from this replica computation. So you start with f at the highest level, and then you have a sequence of parameters, and you define recursively down functions fj, where fj minus 1 depends on, fj depends on j variables, and you're getting just that out from integrating fj in this way here. So where this is a normal distribution, so you come down from fk to fk minus 1 up to f0, which is a real number here. And then we define Parisi equals to that. Now this is exactly the Parisi formula, except that this term is different. So in the Parisi formula for Sherrington-Kirkpatrick, this is a quadratic functional in MK. So only that is different. So this is exactly like in the Parisi formula. And then the theorem we have is that our solution of the variation formula is given by the infimum over this Parisi functional. So, and then the situation where you have high temperature, so corresponds that you don't have replica symmetry breaking. And the full replica symmetric picture would be if these parameters are all different here. So now, okay, I had our first slides, but I'm now really out of time. So the point is, okay, just in words. So what comes out is that the dependence on this structure is first highly okay. It depends in a very non-trivial way on the temperature parameter. Furthermore, what turns out is that if the temperature beta is different from beta prime, the ultrametric structure is completely reshuffled, like what is claimed in the Sheridan-Kirkpatrick model. And the overlap, if you pick two at different temperature is 0, so you have this chaos property. And secondly, the proof of really that you have this hierarchical structure, which is the only thing which is really new, is depending on an extremely delicate way. It's much more delicate than this large deviation business, which is giving the free energy. So because it amounts to introducing some kind of random temperatures on the intermediate level, just to get really the decoupling of the different levels is much more delicate. So now you see, this is really the whole model is certainly a toy model still. So, but my feeling is that, okay, it's already quite complicated. But my feeling is that if you want to do something for real spin glasses, one has to go to something like that. So that's a bit my feeling. So we are happy that we have a model which shows some things which are much more delicate than just in the generalized random energy model, and hope that in the end, okay, might be helpful to get better understanding of the real issues. So sorry for being over time. So.
Very interesting. Any questions? There were some already, but unexpectedly somehow. In the first talk, we see that we go in the direction of finding a simpler model which somehow simulates something we expect in a real model, in the original one. And here is also this thing. It's an interesting development. It's just an opinion. And yeah. Anyway, if there are no more questions, let us thank the speakers of this session.